All right, hello everyone. Welcome to lesson 3.5. Today we're going to be talking about how to take derivatives of inverse functions. We've seen a good number of our basic functions, trig functions, exponential functions, polynomial functions, rational functions. We know how to take care of those, and composite functions, and a few other ones as well, but we haven't talked at all yet about inverses, inverse functions, kind of in a direct way. So I want to address that today. Some reminders. What is an inverse function? Well, an inverse function is a function that takes all of the assignments of some function we can call f, which might do a to 3, b to 1, c to 2, and reverses that. It would assign a to b, 1 back to b, just like b went to 1. It would assign 1 back to b, 2 back to c, and 3 back to a. So the inverse takes all of the outputs of f, they become the inputs of the inverse, f inverse, and the outputs take us back to where we began in f. And essentially, they invert or undo all of the operations of f. We can think of it like this little function machine here. An apple goes into function f, and we get lemons out, and then the lemons go into the inverse, and we would return it back to apples. All right. One thing to be aware of, though, is that f inverse, this notation, does not mean 1 over f of x. We're not talking about exponents here, we're talking about the inverse of f. In other words, the function that takes the y values of f and reassigns them back to the original x values. We put f inverse of x here, and we can put anything in for x here, and it'll reassign it back to whatever the input of f would have been. All right, but this is not an exponential function. Graphically speaking, inverses really are a reflection of the function f of x over the line y equals x. We are basically switching our x and our y values here. If you switch your x and your y values, you go from the function f to the function f inverse of x. So let's review real quickly the algebraic process for finding the inverse function, f inverse of x. We want to find f inverse of x if we know f of x is x cubed plus 1. Well, to make things easier, I like to first rewrite things as y equals x cubed plus 1, keeping in mind that f of x is simply y. All right? Now, first thing we do, since our inverse function switches our x and our y's, we're going to do that. I'm just going to switch the location of our x and our y variables. Now my job is to resolve for the new y value here. I can subtract 1. Now I can take the cube root of both sides. And there we go. This thing I'm looking at here, is the inverse function. This really is now f inverse of x. It'd be the cube root of x minus 1. And we can do a quick check. If I plug, if I plug 2 into here, x equals 2 into here, I would have 2 cubed, which would give me 8, plus 1 will give me 9. So when x is 2, my y value is 9. Let me go ahead and plug 9 into here. 9 minus 1 will give me 8. The cube root of 8 is 2. And oh, look, I got back to where I began. This is my inverse function. So if I want to take a derivative of an inverse function, f inverse of x at some point, a couple ways we could do it. One is we could actually, I should say simply, find the inverse function and then take and evaluate its derivative. So, if possible, we can just find the inverse function and take its derivative. This is best when it's easy to actually generate the inverse function. If we can find that inverse function pretty quickly, then we can use this step. We basically find the inverse function by exchanging the x and y's and solving for y's. Then we take the derivative of the new y. This is the derivative of the inverse then, since we're taking the derivative of that new y thing. This is the derivative of the inverse. And then we'll plug in the given c value to find the derivative of that inverse at some value. So let's find the derivative. Let's find the derivative of the inverse function f inverse of x at x equals 9 if f of x is x cubed plus 1. Well, we already went through the process of finding that inverse, right? We switched the x and the y's. And after solving this, we found that the cube root of x minus 1 is y. So that's actually our inverse function like we saw above, right? Our inverse function is the cube root of x minus 1. Now I have the inverse. I want to take the derivative of the inverse function. I have found the inverse. So now let me take its derivative. So the derivative, should not say equals, the derivative of f inverse of x is going to be equal to, now f inverse of x, I have a cube root there, so I can rewrite this as x minus 1 to the 1/3. And oh look, I'm going to have a chain rule thing. I have an inside and an outside function. So the derivative of this inverse, which is up here now, is going to be, I'm going to bring down the power, keep the inside, subtract 1 from the exponent. Derivative of the inside, oh, that's actually just 1, so I don't even need to multiply by 1 because it doesn't change anything. So here's actually the derivative of our inverse. If it helps, we can rewrite this as 1 over 3 negative 2/3. So that's going to be the cube root of x minus 1 squared. It flips to the denominator because the negative sign, the over 3 is still a cube root. The squared becomes the power on the x minus 1. So here would be another way we could think about the derivative of this inverse. So what we now have is the derivative of the inverse. We want to evaluate it at x equals 9. So I can plug in that I'd have 1 over 3 times the cube root of 9 minus 1 squared. All right, if I simplify this, I end up with 1 over 3 cube root of 9 minus 1 is 8 squared is 64, right? 64. The cube root of 64. The cube root of 64, right? 4 times 4 is 16 times another 4 will give me 64. So this would be 1 over 3 times 4, which will give me 12. All right. If you recall, you can also take the cube root first and then square things. So this would be the cube root of 9 minus 1, which would be 8. Cube root of 8 is 2, squared is 4. 4 times 3 will give us 12. And there we go. There is the derivative of the inverse function at 9. But we first found the inverse function, then took its derivative, and then plugged in 9. This method is best, like we said, when the inverse is easy to find. But there's lots of functions where the inverse is actually not particularly easy to find. So what do? There's a nice rule that actually helps us around some of these situations where maybe the inverse is not particularly easy to find as an expression or as an equation. We use this general rule when taking the derivative of an inverse. F inverse prime of x is, we follow this, 1 over f prime of f inverse of x. Let me show you how this works. Let's suppose we know these things. F of 1 is 2, f prime of 1 is 4, f prime of 2 is 13. And we want to determine the derivative of f inverse of 2. So here's how I write this kind of stuff out. If we want f inverse prime of 2, I'm going to follow this equation up here. 1 over f prime of f inverse of 2. I'm just going to follow this to its logical conclusion. So this means I need f inverse of 2. I go, well, what is f inverse of 2? This isn't a derivative. F inverse of 2 is saying if I plug in 2 into the inverse, what's my answer going to be? But think about how an inverse works. An inverse switches the x and the y value. So if I'm plugging 2 into the inverse, this would be like a y value of 2 on my f graph. Oh, look, here's a y value of 2 on my f graph. So f inverse of 2, if I want to undo that for f, I want to go from 2 back to 1. Remember, an inverse flips or changes our x and y value. So f inverse of 2 is 1. I can tell from here. The output of f at 1 was 2, so f inverse of 2 takes us back to 1. So this is going to be 1 over f prime of f inverse of 2 we just decided was 1. It's that x value that had a y value of 2 in our original function. So f prime of 1. And then we go, well, what's f prime of 1? Well, f prime of 1 we know is 4. So this would be 1 over 4. And there we go. That would be our derivative of f inverse at 2. Not too bad, right? Let's do another example. Here we want to determine the derivative of f inverse of 6. All right? Derivative of f inverse of 6. So f inverse prime, that's a weird looking And there, f inverse prime of 6 is going to be 1 over f prime of f inverse of 6. So I go, okay, well, what's f inverse of 6? I'm given a lot of information up here. F inverse of 6. Some of these last two have to do with derivatives, so it's not those. F inverse of 6. It's not this one. That would be f of 6. We want f inverse, so we go backwards. The 6 is our y value. F inverse of 6 is 3, so this gives us 1 over f prime of 3. F prime of 3 is negative 1, so this gives us 1 over negative 1, or negative 1. And there we go. All right, so we've seen a couple different examples now. What I want you to do actually is to pause the video and try these 3 problems, and then come back and check your work, please. All right, let's do it. We want to find the derivative of the inverse function at x equals 1. Here's f of x. All right, so first, since we're given this function, this looks like something we can actually find the derivative, the inverse pretty easily of. So let's do that. Y equals the cube root of x minus 1. To find the inverse, I switch my x's and my y's. Now I start solving. I get rid of the cube root by cubing each side. Gives me y minus 1. This gives me x cubed plus 1 equals y. There we go. So now I have my inverse. I need to take its derivative. Its derivative then will be 3x squared plus the derivative of 1 is 0. So 3x squared would be my derivative there. And I want to find the derivative of the inverse. Here was the inverse. I just took its derivative. And I want to find the derivative of the inverse at x equals 1. So all I have to do is plug in 1. And that'll give me 3 times 1 squared, or 3. There's the derivative of the inverse. Not too bad. Well, let's suppose we have this given information. And we want to determine if the derivative of the inverse at 7, what is it? All right. We get f of 1 is 7, f of 7 is 2, f prime of 1 is 5, f prime of 2 is 10. Let's follow that derivative rule we looked at earlier. So I want f inverse prime of 7. So that's going to be 1 over f prime of f inverse of 7. There we go. So that's going to be 1 over f prime. Well, what's f inverse of 7? F of 1 was 7, so f inverse of 7 is going to give me 1. So that's f prime of 1. F prime of 1 is going to be 5. I see that up here. So it's going to be 1 over 5. All right. And 10. Here we got a table to help us out. Selected values of the strictly monotonic function. This is a new word. Monotonic, all that means is that it is essentially moving in one direction, always increasing or always decreasing. The values of a strictly monotonic function g of x and its derivative g prime of x are shown in the table below. Find g inverse prime of 1. All right, g inverse prime of 1 is going to be 1 over f. Well, not f. We're looking at a function called g now. G prime of g inverse of 1. All right. So g inverse of 1. Well, how do I figure out that? G inverse of 1. This is a y value of g, right? So if I look at g here, where does it have a y value of 1? Right here. So what's g inverse of 1? Because remember, an inverse switches the x and the y. So that's like a y value on g. G inverse of 1 is negative 1. So this becomes 1 over g prime. G prime, I'll fix that. 1 over g prime of negative 1. Now we go, what's g prime of negative 1? G prime of negative 1 is negative 1/5. So this becomes 1 over negative 1/5. Because g prime of negative 1 is negative 1/5, which, I'm running out of space here, 1 divided by negative 1/5 is negative 5. There we go. That'd be g inverse prime of 1. What about g inverse prime of negative 3? Similarly, we could do 1 over, that'd be g prime of g inverse of -3. All right, we work through this 1 over g prime of g inverse of -3. So g inverse -3, that's like a y value on g. Where does g have a y value of -3? G inverse of -3 will be 4. So this is g prime of 4. G prime of 4 gives us -2. So this is 1 over -2, or -1/2. And there we go. Not too bad. These derivatives of inverses actually come up every year on the exam, and historically speaking, they've actually been the last multiple choice problem on the first section of the exam. Just to put that into your brain for a second. All right, here's what I'd like you to do. To practice this idea, I want you to do the first page of the homework here, okay? Read carefully, make sure you understand what is being asked in each problem. When you do the first page, that's page 28. Everyone has to do that, and then you'll check your work and check your work, correct your answers, and upload your corrected work to the assignment you'll see on Google Classroom. So everyone has to do that. There's also some optional homework here I encourage you to do if you have time. Then, after you've done the required homework and corrected and uploaded your work, there's a 5-question little check-in quiz I want you to do about implicit differentiation, like we were doing in class. Some big topics. I want to make sure we're feeling okay about it. All right? Recap. Got to do this homework page and the quiz about implicit differentiation. Take that quiz. No notes, please. I want to see what you know right now. Thanks. Have a great day.